In this video, we're going to talk about the distinction between critical points and inflection points and how you find each of those and how you classify them. So first, just a little bit of clarification. What does it mean to classify critical points? It means to classify a critical point, each critical point, as being either a local maximum, a local minimum, or none of the above. A critical point could be neither of those. And for inflection points, we want to determine where the inflection points are and whether each one has the graph transitioning from concave up to concave down or vice versa. So either up to down or down to up. All right, well, how do we find out where the critical points are and where the inflection points are? One thing to remember is that a local maximum occurs when a function's graph goes from going uphill to going downhill, or when a function goes from increasing to decreasing. And a local minimum occurs when a function goes from decreasing to increasing. In either case, that transition is going to occur at a point where the derivative of the function, f prime, is either 0 or undefined. So that's how we find critical points. And then inflection points occur when the concavity of the function's graph goes from concave down to concave up. So that's a point where the concavity changes from down to up, or the graph's concavity changes from up to down. So here we have a change from concave up to concave down. And here we have a change from down to up. What both of these examples have in common is because we know that concavity down indicates that the second derivative of a function is negative, and concavity up occurs if the second derivative is positive. Same thing here. Here, the second derivative of a function is positive. The second derivative here is negative. In both cases, the second derivative had to transition between being negative and being positive. That means that f prime is 0 or undefined. Those are where you might have inflection points. Now, that's not to say that every time we have a critical point that is a 0 of the derivative or a place where the derivative is undefined, that we are necessarily going to have a local extreme. We could have a critical point that looks like this. Could be going up and then stall out for a second and then continue going up. That would be a critical point because there's a horizontal tangent line, but it's neither a local maximum nor a local minimum. And similarly, we could have a 0 for the second derivative, f double prime, without actually having a point of inflection. We could have that happen without an actual change in concavity. So one thing to keep in mind is that critical points are any points where f prime is either 0 or undefined. And then some of those may be local maxima or local minima. We use the term inflection point, though, only when there is an actual change in concavity. So for this, actual change in concavity required. Change in concavity required. But we know to look for those at places where f double prime is 0 undefined. Anyway, let's get on with it. Let's work on this particular function, f of x equals 12x minus x cubed. So to find critical points, we first need to know what the derivative of f is. So f of x is 12x minus x cubed. What is f prime? Well, f prime of x is going to be 12 minus 3x squared. And we need to know when this is equal to 0. We know that it's always defined because it's polynomial. So the only way to get a critical point is if this is equal to 0. So let's see. We have 12 minus 3x squared equals 0. That factors into 3 times 4 minus x squared equals 0. And then I can factor that and get 3, 2 minus x, 2 plus x equals 0. And then that leaves as possibilities that 2 minus x equals 0 or 2 plus x equals 0. The first one occurs when x is equal to 2. Second one when x is equal to negative 2. So these are my two critical points. I will have a 0 in f prime when x is equal to 2. I will have a 0 in f prime when x is equal to negative 2. So those are my critical points. But what kind of critical point is each of those? To find that out, I'm going to analyze when this function is increasing and when it's decreasing by using the first derivative. So I'm going to draw a little number line diagram here. My critical points are at -2 and 2. So those are places where f prime was 0. And now I just need to analyze what happens with f prime on each interval. Well, f prime was equal to 12 minus 3x squared. And that was equal to 3 times 2 minus x times 2 plus x. By analyzing those factors, I can determine whether f prime is positive or negative on each interval. And I'm going to do this in a way that's a little bit slicker than what I did in class. In class, I've probably been testing actual values for x in this formula, one on each interval. I'm going to do one better here and just say, okay, if x is greater than 2, then 3 times 2 minus x times 2 plus x. I know 2 plus x will be positive. 2 minus x is going to be 2 minus something bigger than 2. That's going to be negative. So I can say that is equal to 3, which is a positive number. Let me just write down that that's positive, times negative times positive. That's negative. So on this interval, f prime is less than 0. So f is decreasing. Okay, what about the interval where x is less than -2? If x is less than -2, then 3 times 2 minus x times 2 plus x. Well, this time 3 is still positive. 2 minus x, if x is less than -2, that's going to be positive because I'm subtracting a negative number from 2. But 2 plus x is going to be negative because 2 plus x is 2 plus something less than -2. So that's going to counterbalance it in favor of being negative. So there I'll get a negative number. F prime is less than 0 on that interval on the far left. That leaves the one in the middle. If x is in the interval -2 to 2, then my product is 3, 2 minus x, 2 plus x. 2 plus x is positive because my x is greater than -2, but 2 minus x is also positive because x is less than 2. So this is a product of 3 positive numbers, and that's positive. If you're not confident doing the work that particular way, just thinking in terms of inequalities, test a value. That's usually the surest way to figure out what f prime is doing on each interval. So on these intervals, I wrote down that f is decreasing on the far right, but here f is increasing, and on the far left, f is decreasing. That suggests that these critical points here, in fact, that tells us that the critical point at -2, we're going from decreasing to increasing. That's going to be a local minimum. And the critical point at x equals 2, we go from increasing to decreasing. That's a local maximum. So that's the first part of my question is, I now know there are critical points at -2 and 2. One's a local minimum, one's a local maximum. Now to find inflection points, I'm going to look at f double prime of x. I know that the first derivative was 12 minus 3x squared. So the second derivative is going to be -6x. The only place where that's 0 is when x equals 0. So that's the only possible inflection point. That's the only possible point of inflection. But to find out whether it's an actual point of inflection, then you need to determine whether the concavity of f changes at that point. So I'm going to use a number line diagram to do that. My possible inflection point is at x equals 0. And I just need to analyze whether f double prime is positive or negative on each interval around 0. So if x is greater than 0, then -6x is less than 0 because it's positive times -6. So that means f double prime over here is less than 0. That means f is concave down. When x is less than 0, that means x is negative. Multiplying that by -6 gives me a positive number. So that means that on the left side, f double prime is greater than 0, so f is concave up. So we do have an actual change in concavity here. We're going to change from concave up to concave down. So at x equals 0, that is a point of inflection. There is a point of inflection, which is a change from concave up to concave down. Move that up a bit. And now we have a complete classification of all the critical points and all the inflection points of f.